We now formalize the definition of the limit a little more strongly, and we're going to be using this common form. Limit as x approaches c of some function is going to be a number, let's call it L for limit, if our function gets as close to some value as we want for all the values x close enough to c. So f close to L if x is close to c. And again, this gets pretty technical because, as we said in the last notes, the limit is equal to some number, even though the function itself never does reach that value, or doesn't have to reach that value. So it does get pretty subtle, and again, we would go into more of the theory of this in Math 120. All right. Now, sometimes this number may not exist, and we'll see some examples of that momentarily, and if that's the case, we would say the limit does not exist. All right. Here's a very important distinction to make, and it's going to tie back to our idea of continuity. The limit does not depend on the value, never depends on the value of the function. So if we go back just 1 second to our last notes, the value of the function here, there is no value of the function, in fact. The limit doesn't care. The function could do anything so long as the trend of the curve as we approach our breakpoint is 1. All right, let's explore this further through some examples. Okay, so here we have a graph. There's a hole punched out, and it's that empty circle, which means the function is not here. There's a filled in circle, which means the function is here, and then the function continues on. So in our old terminology, or earlier terminology, this function is discontinuous. We could not draw it all in one pen stroke. We'd have to go like this, draw a little dot, and then continue on with 3 different pen strokes there. All right. Now let's talk about this limit idea. As x approaches 2, what happens to the function? Well, again, x approaching 2 means we come in from one side or the other, and we see, are we close to, well, here we're claiming 6. If it were 6, if the limit as x approached 2 of f of x is equal to 6, then what would that mean? It means that for x values close to 2, f of x would have to be close to 6. Now, is that true? Well, definitely not. If we take x values close to 2, we get output values, y values, that are close to 4. So that's simply not true here, which tells us that the limit as x approaches 2 of f of x is not 6. And again, this goes back to our idea that the actual value of the function of f at the exact point x equals 2 is irrelevant to the limit calculation. In fact, going back to our earlier intuition, what is the limiting value? It's where we would end up at, not where we do in the function, but where the function is trending towards, or where the function would end up if we could continue it as a seamless graph. And let's talk about that for a second. What is the real limit then? Well, as we pick different x values, and as they get closer and closer, where are we going to be located? We're going to be located around f of x, or y equals 4. So the limit here, as x approaches 2 of our function, is going to equal where the empty circle is, or at y equals 4. Now, there's obviously examples where limits do not exist. One example would be something like this. As x approaches 0 here, which is another way to write our limit, what happens to the function? Well, we follow our graph. The function is not trending towards any finite value. And so here's going to be the test. Does it trend towards a single and finite value. It definitely does not. This graph, as we approach from the left, is going off towards infinity. It has an asymptote. As we approach from the right, it has an asymptote as well. So as x goes to 0, this function does not trend towards a single finite value. What do we conclude from that? Well, if we ask the question, what is the limit as x approaches 0 of f of x, we can't set it equal to anything. There's no number we can plug in there. We can't say it approaches 4 or anything else. So we say that that limit is simply undefined. So let's compare and contrast. In this last example, if we followed the graph, we would get closer and closer to a y value that was 4, and continuing the line would end us up at that nice single finite value, and so the limit exists. The limit of f of x as x goes to 2 was a single value. When we have an asymptote at the x value we're interested in, then we're going to have a limit that's undefined. And if we consider an example like this, which we'll study a little later on in the course, we'll give you a formula for it, but if we look at this graph and see what it's doing, what we see is an ever-accelerating oscillation happening here in the graph. So the limit as x goes to 0, in this case here, of our function, it's finite. You know, there's no asymptote here, but the problem here is that it does not approach a single value. So we might be able to say something later on about the range of values, but it certainly does not. I can't pick a value here and say, yeah, it's getting closer and closer to 1, because for any range left to right, I can get any of these 0 to or -1 to 1 values here. I guess I should put a scale on. I can get any of these output values I want. So I can't say there's one single number that we're approaching. And under those conditions, we would have to say that the limit as x goes to 0 of f of x is undefined as well. So it's one single finite number that we get as we trace our graph inwards towards the limit point, or it's undefined. The limit as we approach that point is undefined.